we're going to introduce the correlation coefficient and discuss it in the context of this course. This lesson is titled Pearson correlation coefficient rather than just the correlation coefficient. That's because we want to be precise about which correlation we're referring to. We'll learn about the other types of correlation coefficients later in this course. Most of you have probably heard about the correlation coefficient. It's a term that's pretty overused with loaded meanings in both media and even some scientific literature. For now, the important points to note about correlation are that 1. Correlation does not imply causation, and 2. In the general case, correlation does not imply statistical dependence either. We'll investigate the second point in more detail later, but for now you'll just have to take my word for it. So let's go to the definition of correlation, and that's shown here in this first cell in my Jupyter notebook. I've defined correlation. It's typically denoted with the Greek letter rho between two random variables x and y to be the covariance of these two random variables scaled by the product of their standard deviations. This is shown in the definitions here. You can read these for yourself, and these are just from Wikipedia. This is a standard definition of correlation coefficient. So this is the theoretical definition, and it involves using the random variables. But suppose we have a set of samples and we'd like to estimate the correlation coefficient. Well, in that case, what you'd do is you'd use this formula right here, which is an estimator. Here, the numerator is a product of each sample in the data set that is centered. Centered is another word that means removing the mean from each sample, and the mean of each sample is denoted by the bar over it, the sample mean. By multiplying the centered samples and summing them, we can see kind of a pattern that emerges. If both of the centered samples are large, then the product is large and the overall sum will be large. But if both samples are small, then the product decreases. Or if one is positive and one is negative, this turns into a negative value. So this is kind of an intuitive way to think about why this measures covariance. And covariance is intuitively what it sounds like. It is how these two variables vary with each other. And the denominator here is, again, it's just an estimator of the standard deviation of x and the standard deviation of y given a set of samples. So let's go through a couple of quick examples to understand how the correlation coefficient can help us do some data analysis. Here we have the wine data set again, and I've plotted the alcohol content of the wine versus the proline content. And proline, just FYI, is an amino acid present in grape juice and wine. So we see a pretty strong correlation here of R equal to 0.64, and you can see how I've estimated that. I've just used NumPy to estimate the correlation coefficient, which performs a numerically stable version of this equation that we've shown here as the estimator. So let's take another example, again with the wine data set. Now I want to compare the alcohol content to the magnesium content in a wine. And here I've done the exact same computation, and we see that the correlation coefficient is 0.27, which is a lot weaker than 0.64. Before we end this basic introduction to correlation, I wanted to go through a little bit of a deeper meaning of what correlation coefficient is and how it's related to other concepts that we'll be touching upon later. So the correlation coefficient is intimately related to the multivariate Gaussian distribution. So let's look at the formula for the probability density of a bivariate Gaussian distribution. Bivariate just means two random variables. This can be extended to as many random variables as you'd like. So notice here that in this formula, that the correlation coefficient denoted by rho appears in several different places. Right here in the denominator, again here. And the other terms you're familiar with, the standard deviations and the means. So this is the formula for the probability density function for a bivariate Gaussian distribution. And we see that the correlation coefficient is a term that is used to define this distribution. So this is a statistic that is part of the definition of the multivariate Gaussian distribution. Um, so how does this actually look? So I've created several plots here which show what the contour plot of a multivariate Gaussian distribution, in this case bivariate Gaussian distribution, looks like as I vary the correlation coefficient from negative 0.9, which is a strong negative correlation, to a positive 0.9, which is a strong positive correlation. Intuitively, what you can see from this is that it's kind of controlling the rotation of this Gaussian distribution, um, and a little bit of the strength, but other factors control that as well. That's not really pertinent to this lesson. But what's important here is that it's kind of a direction of which way the vector or the Gaussian distribution is pointing. So in the negative case, it's going from top left to bottom right. And in the strong positive case, it's going from bottom left to top right. And it varies in between. So the standard deviations and other variables here control the other factors of this distribution, how fat it is and where it's centered. In this case, I've centered all of it to 0, just for purposes of explanation here. But that's the end of this lesson. It was just a quick introduction to correlation before we start moving into why the correlation coefficient may have some deficiencies and ways to overcome that using copulas. That's kind of our roadmap. And thanks for watching. I'll see you in the next video.